Top of the morning to you. We are going to continue the August 2016 Algebra 2 Common Core Regents exam. This is the second video. We have already done problems 1 through 8. On today's video, we are going to do problems 9 through 16. I always say good morning because every time I do these videos, it's roughly, 8:45 a.m. my time. I never, walk into school all depressed at 7 p.m. and down and do them at night and say, hi, good evening. This is Mr. Visca. So let's go ahead and start these problems. Just figured I'd explain that. Let's jump right in. Number 9 states, all right, Kristen wants to increase her running endurance. According to experts, a gradual mileage increase of 10% per week can reduce the risk of injury. If Kristen runs 8 miles in week 1, which expression can help her find the total number of miles she will have run over the course of her 8-week training program? Now, with a calculator, okay, if you're going to do 6 weeks, okay, for week number 1, okay, 2, 3, 4, 5, 6, okay, week 1 was 8 miles, okay, those increase by 10%, so this will be 8.8 and so forth. Okay, you can figure out what those are, add them, and then actually put number 1 in the calculator and see if you get the same total. And you can try and put number 2 in the calculator and see if you get the same total, whatever. All right, so that's a shortcut way to do this. I'm going to show you the algebraic way, which would be good in case there's a short answer. First of all, we need to understand, we need to come up with an expression, all right? I see these two things, and a geometric series, that is in the reference sheet, okay? So let's take a look at 3 and 4 for right now. On the reference sheet, you have A1, which is your starting amount, minus A1 times your rate. And rate is really 1 plus rate here. That's really your B value. I can't stand that they use an R. Okay, raised to the N, all over 1 minus that same B or R value. All right? Right now, if I were to do this, okay, I'd have 8. I'd start with 8 minus 8 times 1.10 because it is increasing by 10% or 0.10. That's where I get 1.10 to the N, all over 1 minus 1.10. If I look at the denominator on these, if I actually simplified that, I'd get negative 0.10 on the bottom, right? This is not negative 0.10. Neither is this. That's bad. Okay? That's bad. All right? So it is not 3 or 4. We are immediately down to either 1 or 2. And the only difference is we need to come up with sort of a geometric sequence. Okay? A geometric sequence to put into our summation. So it's either this or this. Okay? You'll notice both summations go from 1 to 6. Okay? So we just need to figure out what is the sequence that would give us that expression next to the summation. I'm going to erase this right here. Okay? So we have some space to work. Bang, bang. And here we go. Okay, so if I know my first term is 8, okay, my second term is 8.8, okay? How did I get that? Because it's increasing by 10%, okay? I have 1 and I'm increasing it by 10%. That's 1.1. So if I multiply 8 times 1.1, 1.10 if you will, and so forth. All right, so a geometric series says I take my first term, multiply it times my rate, and raise that to the n minus 1. Okay, so I have 8 times 1.10 to the n minus 1. This is the sequence that I have to add up from week starting at 1 to when week hits 6. Okay, and that is clearly choice 1. The big thing here, your exponent isn't n. Okay, it's n minus 1. All right, there you go. Lovely, lovely trig question for number 10. It says a sine function increasing through the origin can be used to model light waves. Violet light has a wavelength of 400 nanometers. Over which interval is the height of the wave decreasing only? All right, you need to know a couple of basic things here. All right, basic, and they're going to help you. Let's start with sketching this thing. All right, so a sine function. I know a sine function, that's my S curve. All right, that's my S curve. So I know at some point I'm going to draw the sine curve. I don't know if it's, the question is it going to go up like this? Or is it going to come down like this? Okay. Well, increasing through the origin. Increasing means it has a positive slope. My red line is a positive slope through the origin. My blue line is going down through the origin, so I don't want that, okay? So let me just undo all this poo-poo. If it is increasing through the origin, I know it should be coming up through the origin, and now I do my sine curve, my S. First thing, okay, it can be used to amount, it says it has a wavelength of 400. That means one length is 400. Half of 400, 200. If this is 0, that means my high point is at 100, and my low point is at 300. Okay, I'm literally blocking those off. All right. Now, they want to know which interval is the height of the wave decreasing only. Okay. So I got to look to see where this function is decreasing. That means it has a negative slope from here to here. Let me do that. Oh, I love to use highlighters. Oh, blue. From here to here, that's decreasing. That's from 100 to 300 is decreasing. Boom, choice 2. From 100 to 300. All right? Pretty simple. You just had to know some basic properties about a sine function. Number 11. The expression x cubed plus 2x squared plus x plus 6 is equivalent, divided by x plus 2 is equivalent to what? This is a division problem. I can use reverse tabular. I think I used that on last exam. I don't even know, maybe even earlier in this exam. I did the June 2016 exam and did reverse tabular. I'm going to use synthetic here. Because I'm dividing by 1x plus or minus something, I can use synthetic. So if I have x plus 2, and I solve that for 0, like I was booty cheeking this, I get x equals negative 2. That is what I'm going to divide in. Now, when it comes to synthetic division, just a quick little reminder, I just want the numbers. I don't want the x's. This is 1x cubed. That's a 2, positive 1, positive 6. All right? So let's not forget that's a 1. I'm going to bring my 1 down. A 2. That's another 1. And that's a 6. All right? Now, keep in mind, I didn't say this out loud, but you always need to check. I mean, I checked this in my head. I am not missing a single term up here. I have x cubed, then I have, that's a power of 3, power of 2, that's power of 1, that technically has 0 x's, good. That's 1, that's 0 x's, good. I'm not missing any terms, so I can go ahead and do synthetic division. I draw my line. Okay, yep. Always start by dropping the first term, and then it turns multiplication, addition, so forth. Negative 2 times 1 is negative 2, and I add them. Okay, so I always take my products here and I add them. 2 and negative 2 is 0. Now I multiply negative 2 times 0, and I get 0. I add them. 1 and 0 is 1. Negative 2 times 1 is negative 2. When I add them, I get 4. This is my remainder. My remainder is positive 4. So what does everything else here represent? This would be 0 x's. This would be x to the 1. This would be x squared. So I have 1x squared, no x's, and plus 1. Then my remainder is a positive 4, and I always put my remainder over what I divided in. That happened to be x plus 2 is what we were originally dividing in, wasn't it? X plus 2. So I divide that by x plus 2. And my answer, that's exactly what choice 2 is right here. Boom. Easy. You could have used reverse tabular. It would have been just fine. All right. But I think synthetic is a lot easier as long as your divisor, the number you're dividing in, okay, as long as this thing right here, as long as that's 1x plus or minus something. That makes it a lot easier and less complicated. If that was not a 1x, I would not have used synthetic. I would have used reverse tabular. But you pick your poison. Reverse tabular works for everything. That's why some people always like to do that. Number 12. This one is a data or stats problem. A candidate for political office commissioned a poll. His staff received responses from 900 likely voters, and 55% of them said that they would vote for the candidate. The staff then conducted a simulation of 1,000 more polls of 900 voters each, assuming that 55% would vote for their candidate. The output of the simulation is shown in the diagram below. Now, I'm looking at this graph they have, and it says, given this output and assuming a 95% confidence level, this right here, okay, is important. It says the margin of error for the poll is closest to 95%. I preach this. That's the moneymaker. That's always the mean plus or minus 2 standard deviations, okay? That should cover 95% of this. Now, look here. This is the average they use, so that would be the mean. They did not say this is 1 standard deviation, okay? These are just labels. There is nowhere on this graph where it gives me the standard deviation. So I really can't use this, okay? So what they're saying is my margin of error, in my opinion and interpretation of this, that's telling me how far from the average can I go, okay? How far from the average can I go where it would look like it covers 95% of all that data, okay? So for example, let's take a look at choice 1 here, 0.01. I will do this one in red. If I add and subtract 0.01 to my middle, I'd get 0.56 and 0.54 from here to here. Does that look like it covers 95%? No way. That looks like it barely covers 50%. That's not an option. All right. Let's look, and I'm going to go to the far extreme. Let's look at this one, 0.12. If I add 0.12 here, that would be 0.67, which is like way out here. And if I subtract 0.12, that'd be 0.4. Oh my God, is that 4.3? That'd be way out here. This doesn't cover 95%. That covers 100%. That is not 95%. Remember, 95% is still going to leave some on the outer edges that are not in our interval, okay? All right, let's look at the next one here. Let's do this in purple. 6. Okay, if I add 6, that brings me right here. 6.1. If I subtract 6, it brings me right here. Again, that covers 100%. That's also 100%. It's not 95%. That's all of our data in that bounds. But if we look at 0.3, which I'm going to do in yellow, which by process of elimination is our answer. 0.3, if I add it, goes to 0.58. And if I subtract 0.3, it goes to 0.52. Okay, that looks to me the closest to representing 95% of my data. Okay, that was a tricky one. Okay, but again, that comes to understanding that 95% is the common occurrence, right? That's 2 standard deviations away. That covers a majority of your data and just leaves a little bit on the outside that you don't cover. All right, again, they didn't want that exact. They just wanted closest. And again, that's choice 2. Number 13. An equation to represent the value of a car after T months of ownership is V for the value equals 32,000 times 0.81 raised to the T over 12 exponent. Which statement is not correct? Again, I say this every single time. 3 of these will be correct. So if you look at choice 1 and it happens to be correct, all right, then, you know, don't circle choice 1. Which statement is not correct? Okay. So let's take a look at this. And I'm going to tell you right now, there is one thing that confuses people when it comes to these types of exponential problems. This is an exponential problem because the variable is in the exponent. All right. That t represents month. T is not in year right now. If I wanted, okay, if I wanted to get months alone, if I have 32,000 times 0.81, let's call this, okay, t over 12 is the same thing as saying 1/12 times t, right? So I'm going to say 1/12 times t. Okay, if I truly want to know the percentage of increase or decrease, I need to get my variable alone for the exponent. So I'm going to take that 1/12 and I'm literally going to apply that to 0.81. So now I've got 32,000. There's going to be some value in here that I need to calculate. It's a t. Now this is in months solely, and your increase or decrease rate will be in this green parenthesis. So I'm going to take my calculator. Ooh, look at that, fancy. I'm going to take 0.81 and I'm going to raise that to the 1/12. All right. Let's call that 0.98 because all of our decimals, okay, all of our decimals that they give us are 2 decimal places. So 0.98. So now if I want to know how much value of the car, all right, let me do this. Let's get this out of here. All right, if I want to know how much the car increases or decreases per month, this is what it tells me. All right. That is 1 minus 0.02. 1 minus 2% gives you 98%. So it's a decrease of 2% per month. All right. So now that I've done that, let's take a look at our options. The car lost approximately 19% of its value each month. Okay, right there. They're assuming you're going to look at this and say, yeah, 1 minus 19% gives me 81%. That must be true. That is not true, because if you are going to look per month, you need to get this t alone. Per month, we lose 2%. That is absolutely false. All right, let's go over the rest of these to ensure that they are true. All right, and that's where they get you. Not knowing to separate that exponent in the exponent. Okay, not separating that variable in the exponent. There you go. That's what I meant to say. 2, the car maintained approximately 98%. Yes, this is how much it maintains. If it loses 2%, it keeps 98% per month. This is absolutely true. The value of the car when it was purchased is 32,000. This number, your A value, that's your initial investment. That's what the car cost. Yes, that is true. The value of the car 1 year after it was purchased is 25,920. Okay, we're going to have to use our calculator to just make sure that's right. Here is my equation per month. How many months are in a year? There are 12. All right. In fact, if you want to use this one, we can use this one. Why am I going to use this? Because this is rounded. Okay, that's a rounded. It really should be this whole big thing. This is not rounded. So I'm going to use this. Okay, I'm going to make my t in months 12. All right, so I'm going to say 32,000 times 0.81 raised to t divided by 12. T is months, and there are 12 months in a year. And I hit enter. That is 25,920. That is exactly what they said here. That is true. Now, if you're a little confused why I didn't use my 0.98, let's go ahead and do that. Let's take this, hit enter, and let's see what happens when I put a 0.98 here. It'll be close. I hit enter. Ooh, yeah, huh? 31,000. Oh. 12 divided by 12, that's 1. Yeah. I would have to do this. You guys. Okay. I have to change something here. If I use this equation, my t is in months. I just put a 12 here. It's not 12 divided by 12. It's just 12 months. So I do this, hit enter. 25,110. And you might say to yourself, well, Visca, that seems off. Well, it is off because this 0.98 right here, okay, this thing that I'm hitting right here, shouldn't be 0.98. We just rounded it. It should be this thing right here. Where is it? That's the whole thing. So I'm going to hit enter. All right. And I'm going to take this whole thing, 32,000. I'm really going above and beyond for this problem, but I really want you to understand it. I'm going to take this decimal, put it in here, and raise that to 12. Now that's not truncated at all. That should be a lot closer to, yep. That was raised to 2. $25,920 exactly. Wow. Craziness. All right, craziness. Put a lot of explanation into that when we could have stopped when we found out the first one was false. Yeah, what are you going to do? An odd function, number 14. Which equation represents an odd function? All right. This is one of those miscellaneous ones, and it's really testing you whether you know what an odd function looks like. And I don't know. I think it's kind of a garbage question to put on a final. All right, because you barely touch on this in class. But an odd function, okay, here's a set of axes here. If I have an even function reflects across the y-axis. That's even because it's a perfect reflection across the y-axis. It's a mirror. This acts like a mirror, okay? That's even. If they wanted to know odd, okay, odd reflects about the origin. It's like a 180-degree rotation. An odd would look like this, okay? Because it looks like it's a 180-degree rotation. Boom, okay? But more importantly, this point right here reflects across the origin to this point right here. This point right here reflects to the origin to this point right here, so forth. I can go on forever. All these points reflect through the origin, okay? So it kind of has to have like a 180-degree rotation about the origin. So I can put all these in the calculator, but there's only one that's going to look like that. Sine. Sine is our S, remember? If I were to continue it, and I rotate this 180 degrees, oh my God, where did it go? Wow, that was weird. Bam. This point reflects through to this point. This point reflects to this point. This point, oh, we're barely going to get to it, reflects to this point right here. I think you understand. That's the only one that does that. Now, you might say, well, what about cosine? Cosine reflects. Cosine reflects. Cosine is this, the cup. Cosine reflects across the y-axis. So cosine is even. Okay, this reflects to this, okay? This reflects to this, all right? So cosine is even, but they're asking for odd. These two, if you graph them, you're going to notice they don't do that at all right? So the answer is choice 1. It is odd. Number 15, the completely factored form of 2d to the 4th plus 6d cubed minus 18d squared minus 54d is one of the following. Now, I have said before, whenever they ask you if an equation is equal to something else, you can graph them. If their graphs are the same, then they are equal. The same thing goes here. I could put this into y1 There's a catch with this one. And then I can try this in y2. If it's the same graph, there you go. That's it. If it's not, then I'll try this in y2. If it's the same graph, there you go. And I can try all these into y2. But there's one word here that makes this maybe not happen. Factored completely, which means one of these can be factored, but not completely. Maybe this is factored, but it's not completely factored. Maybe it's this one. You see what I'm saying? So you might get two graphs on here that look exactly. One of them is factored, but the other is factored completely, okay? One of them might be a factored version, but it's only partly factored. For example, the first thing I'm going to do here is I'm going to factor, I can take a d out of every term, but I can also take a 2 out. So I'm going to factor out a 2d. That leaves me with d cubed minus, plus 3d squared minus 9d minus 27. Now, if I were to graph this into y1, and I were to graph, yep, that's a 2, a y2, and I graph this into y1, the graphs would look the same. But this right here, even though it's factored, it's not completely factored, all right? And that's what I was trying to say about you may get two graphs that look the same. You got to just pick and know which one is factored completely, all right? So let's continue. Anytime I'm factoring, all right, well, this is good. They all have a 2D pulled out. Okay, so I can't eliminate anything yet. Anytime I'm factoring and there's not three terms like a quadratic, like if I didn't have this, I can booty cheek that, and I can even factor a 3 out of that. But anytime there's four terms, I need to do factor by grouping, okay? Factor by grouping, all right? And what does that tell me? This 2D just comes along for the ride constantly. What's left? I want to take a d out of this. Actually, I could take two d's, d squared. That leaves me a d plus 3. I want to try to factor something out of here that would also leave me a d plus 3. And if I take out a negative 9, it would do just that. Okay? So now, as all factor by grouping does, okay, I am going to, 2d comes for the ride, 2d. Now, I take d squared minus 9. That goes in one parenthesis. And these go in one other parenthesis, not two, just one like that. Now, if I look at this, that is choice 1. But guess what? Even though this graph right here, if I were to put this in y1 and I put this up here in y2, even though they look the same, this is not factored completely. Okay? It's not factored completely. All right? How come? Because this can be factored again. All right? That's a difference of perfect squares. So right now, I know it's not this. I know it's not choice 1 because I can factor this again. Okay? Whenever something's completely factored, I can look and say, hey, I can factor that. I can immediately cross that off. Okay? It's either going to be 3 or 4 at this point. All right? So let's go and continue this. I still have 2D coming along for the ride. We ain't losing you yet. This is a DOPS, a perfect difference of perfect squares. I get d minus 3 times d plus 3. That is just this factored. I still need this as well. D plus 3. Okay, oh, I see what they did there. All right. They rewrote this as 2d. Instead of writing this side by side, they wrote d plus 3 squared, and then I have this d minus 3. That's like saying instead of writing 5 times 5, you can just write 5 squared, and that's what they did. Okay, so my answer is 3. So the funny thing about this is if I were to use the graphing calculator and put this into y1 or y2, whatever, both this and this would have the same graph. The only difference is this one's completely factored because this is a difference of perfect squares. It can be factored again. Number 1, even though it's equal, is not completely factored. It's a great problem. All right, Trig. And really with trig, this really doesn't deal with sine or cosine as much, number 16. It deals more with knowing your conversion from radians to degrees. Now, which diagram shows an angle rotation of 1 radian on the unit circle? Now, here is what people do. And I'm going to be honest with you. It's what I did when I first did this, because you see something, you think you can do it quickly, and you do it, and you're screwed. Okay? Which diagram shows an angle rotation of 1 radian? When you think 1 radian, you're like, oh, well, 1 pi radians is equal to 180 degrees, so it's choice 3. No. This says 1 radian. It does not say 1 pi radian. We always think as in 1 pi is 180 degrees. Okay, don't fall for that little simple trick. If I have 1 radian and I want to make it into degrees, don't I divide that by 100? What's happening? What's happening? Okay, how do I go from radians to degrees? Okay, I multiply by 180 over pi, or do I multiply by pi over 180? One of these, and this is what you got to remember. One of these goes from radians to degrees, and one goes from degrees to radians. Okay, this one right here is if you want to go from radians to degrees. All right, this one here is if you have degrees and want to go to radians. Okay, we have radians. I want degrees, so I'm going to use this one. Okay, so I'm going to take the number 1, and I'm going to multiply it by 180 over pi. Anything times 1 is itself, right? So what I'm going to do is I'm going to go to the calculator, and I'm actually going to put 180 and divide it by pi. Okay, I can do that because, hey, I'm a smart individual, and you are too, and hopefully this calculator turns on. How many times do I have to press on to turn the calculator on? Click, 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 click. There you go. Okay, so I'm going to take 180. Holy cow. Divide it by pi. Pi is the blue icon picture here above the caret. So if I hit second, yeah. That's 57 point, let's call it 57.3. It's about 57 degrees. So, and this is going to make us a lot easier once we do this. 57 degrees, which you can see this is 180, right? This is 90, this is 180, 270. That is not this one. It is obviously not that one. First of all, 57 degrees is in the first quadrant. It's between 0 and 90. It's probably somewhere around here, right? You should look for something that looks like that. Oh my God, look at that. 57 degrees. That's your best approximation. This is 90 degrees. This is 360. Okay? So once you realize, if I can convert 1 radian to degrees, and don't fall for the mistake that it's 1 pi radian, it's not. There's no pi here. And you know which one you're using. It really, take 180 divided by pi, it's 57.2. Well, 57.3 if we round it to the tenths. We are done. Okay, I will see you for the third video, which would be, I don't know, 17 through 24, something like that. All right, see ya.